Hello, everyone. It's me, Billy Younger, again with Physics Solutions, and I am writing another or creating another vector video, not unlike the one where I titled it "The World's Greatest Vector Addition Problem." Specifically, I'm going to actually make a series of videos showing you step by step how to add vectors, and I'm breaking it up into small slices so that we can understand each little part one by one in short videos, so that you don't have to sit down and watch a big vector addition problem in one whole setting. And in doing so, I'm going to introduce coordinate systems. I'm going to show you the different ways you can specify the directions of vectors and the different coordinates you can use. And we'll even talk about coordinates in general, how you can use them to your advantage to make certain vector problems a lot easier. In doing that, like I said, I will make a whole series of videos, and this is the first one, and it's going to be vector addition part 1, and I'm going to talk about coordinates. So let's start. I'm going to turn on my document cam. And I want you to notice this is a typical XY coordinate system. It's not in that great a focus. I'm going to fix that now. Okay, now it's in focus. What I want you to know about this XY coordinate system is normally we draw X to the right and Y up. Of course, if it's a three-dimensional coordinate system, then it needs to be right-handed. So if I put my right hand this way on the X and curl it towards the Y, then my right thumb should point straight up. That's the direction of the Z axis. So if you have to use a three coordinate system or three axis coordinate system, 3 dimensions, then always make sure it obeys that right hand rule so certain other problems don't exist. There's a lot of different ways to specify vectors. For instance, I could draw a vector like this, and I could mark this as 60 degrees and just say, I know that's actually closer to 45, but it doesn't matter. We'll always label it and it's fine. This vector could just be called, if we said its magnitude was, say, 100 newtons. Let's do 100 meters per second, though. So I want you to know all the different things it could be. And we'll call this vector just plain V. So this particular vector could be called vector V is 100.0 meters per second at, and that's just the symbol I often use myself, but I'll say at 60 degrees. If I just say at 60 degrees or at -5 degrees or something, I mean the conventional mathematical phrase for the direction, which basically means that everybody in the mathematics world recognizes this to mean 60 degrees counterclockwise, so counterclockwise from the positive x-axis. Of course, that's not the only way to specify it. I could also go around this way, and since it's clockwise, it'd be negative, and I'd end up going negative 90, negative 180, negative 270, and then this would be another 30, so this would be negative 300. So I could also call this at negative 300 degrees. Okay, again, if I'd made it all the way, it'd been 360. That's why I knew that this is just plate 300. So that's another way I could express that same vector. I could also specify it by realizing that this x-axis corresponds usually to the east direction, and this y-axis normally corresponds to the north direction, and this negative y-axis corresponds to the south direction, and this negative x-axis corresponds to the west direction, in which case I could call the same vector again at 60 degrees east of, or excuse me, 60 degrees north of east, sorry about that, north of east. That's often abbreviated 60 degrees. I like to do NOE, but sometimes people will say at 60 degrees northeast. Okay, but since we already learned this degree right here is 30, remember this whole thing is 90 degrees, so these two have to add up to give you 90. That one's 30 degrees. So I could also say this exact same vector is 60 degree, or excuse me, is 30 degrees, and that 30 degrees is actually measured east of north. So in that case, I'd say east of north, which of course would also be 30 degrees EON, or 30 degrees east north. Okay, so that's another way of doing it. Also, we could actually use this as a compass setup, in which case compasses normally have north as 0 degrees, east as 90 degrees, south as 180 degrees, and west as 270 degrees. So I could also say V is 100.0 meters per second at compass heading of 30 degrees. So the way the compass measures is just 0 degrees. This is 90. This is 180, 270, and you just go from there. So that's another way I could express this. Of course, now you've seen basically just about every way you could possibly specify a vector. Of course, we could also just specify a vector in terms of its components, in which case you might say V has some X component and V has some Y component. But when you're given it in that way, things work out a lot easier. If you're sort of advanced, you can actually say V is equal to the X component, which I'll leave blank right here, times an I hat, plus the Y component, which I'll leave blank right here, times J hat. Those are unit vectors, and they're supposed to point exactly in the positive X direction in the case of I hat, and they're 1 unit, not 1 meter, not 1 meter per second, not 1 Newton, but 1 unit long, and they point in the positive X direction. And then similarly, there would be a J hat vector here too, but that's more for the calculus-based physics classes. They usually do that more so than the algebra-based physics classes. But if you know your 30, 60, 90 triangle, you could probably quickly realize what this is, because the 30, 60, 90 triangle has 60 degrees here, and of course has 30 degrees here, but the 60 degree is opposite the square root of 3, the 30 degree is opposite the 1, and this is opposite the 2. So ours is like that in that we took the 2 and multiplied it by 50 to get the 100. So if I multiply each of these by 50, then I could actually figure out what the individual components are. So obviously the X component is this part right here. That's 1 times 50. So that would be, in fact, 50.0 meters per second. And this one is 1.732, because that's what the square root of 3 is. It's 1.73205 roughly. So if I wanted to look at it that way, it'd be a little hard, because multiplying by 50 is nasty, but multiplying by 100 is easy. So the square root of 3 is 1.73205. And that might not be so helpful, but if you think about the square root of 3 times 100, that's a little easier to do. And I end up just moving the decimal, because there's 2 zeros here. I move the decimal 2 places to the right. I get 173.205 is that actual number. Now, the problem is I wanted to multiply by 50, not by 100. So the square root of 3 multiplied by 50 can be thought of as the square root of 3 multiplied by 50. But instead of 50, we'll make it 100 divided by 2. So now I can say, oh, wait a second, it's the square root of 3. If I can divide that by 2, then I can multiply by 100. And that's exactly what we're going to do, because we happen to know that the square root of 3 divided by 2 is this part right here, is 0.86603. It's actually like 0.25, I think. But anyways, that's plenty enough. So now if I take this and multiply it by 100, 1, 2, I get 86.60. So I'm going to say this component is 86.60 meters per second. So that's the final way you could actually express the vector V in any set of coordinate systems. So I've shown you how to express this 100.0 meters per second magnitude. By the way, the magnitude can be written as V with a vector with absolute value bars on it, or you can just drop the vector symbol and the absolute value bars and just call that 100.0 meters per second. So that's pretty much all the major notation that you need and all the major coordinate ideas you need to understand. This extra part right here is not necessarily something familiar with you. I was just quickly trying to come up with the actual magnitudes of the individual components. And what this means is if I wanted to break this up, or what we call decompose this vector into its x and y components, or what we call resolve this vector into its x and y components, what this tells me is I would have to go to the right, which is a positive coordinate direction, and I would have to go that far or go that way by a distance of 50 meters per second. And actually, I should really be carrying a second decimal place because I was given 100 to 4 sig figs. So I really should have called that way. And not only that, I'm also going in the positive direction and the positive y direction. I just used a different color to show up here. Normally, I like to use green for my positive directions and red for my negative. But since this is 60, we expect the y component to be larger, and that's exactly what we got. In fact, this side is going to require you to go up by 86.60 meters per second in the vertical direction. So all of this is what is entailed in adding of these vectors. This is just the coordinate part. If you happen to be so lucky that like all your vectors are separated by 90 degrees, and here's the last thing I want to say about it, then you can be a little smarter and create a new x and y axis where you make the x-axis, let's call it, say, x prime. It's actually going to be parallel to the actual v vector. So by twisting my coordinate system through 60 degrees, I could say vector v is just this guy, and its magnitude is, of course, 100.0 meters per second, but it's at 0 degrees. That's really a smart move, because whenever you see like all your vectors are 90 degrees apart from each other that you're adding or whatever, then why not switch to a better coordinate system where one of those lies along the x-axis or even the y-axis, and then all the other ones will lie along the x and y-axes as well. So that's just another thing you want to keep in mind when doing vector addition problems. Sometimes the smartest way to do the vector is the easiest way, or actually almost always the smartest way is to do it the easiest way. So you can feel free to twist your coordinate systems any way you want to, so that maybe your vectors lie along the axis. So just keep that in mind. If all your vectors, here's the words I'm saying, if all of your vectors are 90 degrees apart, then what you want to do is set your x-axis parallel to one of them, or set your y-axis parallel to one of them, or something like that. Set a coordinate axis parallel to one of them. So one last time, actually I should have wrote it in there. So one last time, if all your vectors are 90 degrees apart, so for instance, one vector A might be 60 degrees, vector B might be in fact 150 degrees, vector C might in fact be 230 degrees. Those are all 90 degrees apart from each other. So you can say, okay, if all of your vectors are 90 degrees apart, then let's set the coordinate axis, or a coordinate axis, parallel to one of them, and then you won't have to resolve your vectors into components at all. They'll already be along the axes like shown here. So that's the end of part one. I hope this helps you understand how to not only specify a vector in terms of its magnitude and direction, but also all the different ways you can specify its direction. That's it. Hope you have a good day.